Okay, we'll go ahead and get started. Can the people on Zoom see the slide and hear me okay?
Yes.
Thank you. Okay, so what we'll do today is we'll finish up chapter 16 and then we'll start on chapter 17. 17 is more chemical equilibria. And then the other thing I wanted to mention is we will have our next exam a week from today. So next Thursday, we'll have exam number 3. Okay, so we've been talking about weak acids. Now we're going to shift bases a little bit, no pun intended, and talk about weak bases. So a lot of the things and strategies that we talked about with weak acids and determining pHs and things like that, it's very similar for weak bases. Okay, the big difference there, obviously, with an acid, you wind up with free protons, hydrogen ions. With weak bases, it's free hydroxide ions. And so a lot of the things that we talk about with the bases should sound familiar. And so it should be pretty straightforward if you understood the weak acid things. So ammonia is a classic example of a weak base. And we'll be talking about that quite a bit. Hold on here. We'll talk about that quite a bit. And so just as we had acid dissociation constants, we also have base dissociation constants. And we'll see in a little bit what that relationship between acid and base dissociation constants is. As I said before, the equilibrium calculations that we did for the weak acids, it's really a very similar calculation that you do for the weak bases. So if you were comfortable with just how you set up those problems and did those solutions of those problems for the weak acids, you shouldn't have any problems with the weak bases. One interesting thing about bases is that a lot of basic compounds contain nitrogen. And the reason why nitrogen acts as a base is because it has a lone pair of electrons, so a pair of non-bonding electrons associated with it. So in organic chemistry, and so remember when we talk about organic molecules, we're talking about molecules that have carbon in them. So in those types of compounds that have a nitrogen atom in them are referred to as amines. And so amines are almost always basic because of that lone pair of electrons on the nitrogen atom. Down at the bottom here, we have the balanced equation for the dissociation of ammonia. So we see ammonia plus water gives us the ammonium ion and then hydroxide ion. And so we would write that equilibrium expression the same way we've been writing all of our equilibrium expressions, in that we have products over reactants. So in this case, it's the NH4 plus and the OH ions in the numerator and the NH3 in the denominator. So that part should look pretty familiar to you based on what we've been doing. When we talk about weak bases, there's two categories that they fall into. And one is the amines. So remember we said amines were those organic compounds that had a nitrogen in them. And so here's some examples of common amines: ammonia, methylamine, hydroxylamine. For organic compounds, that's a real common weak base. There's also the anions of the weak acids. So remember we talked about conjugate acid-base pairs when we were talking about weak acids. So acetic acid and then the acetate ion. That was the conjugate pair. So those anions of the weak acids, those are weak bases also. Remember, we had that one table, I guess it was maybe about a week ago, that showed acid strength and base strength, and kind of the top was strong acid, and then the middle was weak acid. And to the right of it, we had the conjugate base, and all those weak acids had weak bases associated with them. So when we think about weak bases, it tends to fall in one of these two categories: the amine-containing organic compounds, and then the conjugate bases of the weak acids. Just as we talked about some dissociation constants for different weak acids, here's some for some weak bases. If you look at the structural formula and highlighted in blue are where the proton is added to. And so what you see there in each of those cases in this part of the table, it's that nitrogen with the lone pair of electrons on it has the proton added to it. So what happens is the proton gets added to the nitrogen, and then it has a positive charge at that location. But the other main thing I want to point out is if we look at the Kb values, ammonia 10 to the minus fifth, that's not too low, but we look at these others, pyridine and hydroxylamine, 10 to the minus ninth, 10 to the minus eighth. So those are pretty weak bases. Here's some more. We see methylamine at 10 to the minus fourth. That's a little bit stronger, weak base. And then we see some non-amine type. So there we have the conjugates of some weak acids. Okay, so let's just walk through an example of how we would do some pH type calculations for weak bases. And as I said before, the approach that we take and the way we do it is similar to what we did for the weak acids. So the first thing we would do, in this case, we're being asked to calculate the pH of a 0.15 molar ammonia solution. And so what we would do first is we would write out our dissociation equation. So we have ammonia plus water, giving us ammonium ion and hydroxide ion. So write that dissociation equation out. And then we would write the equilibrium expression. As we've been doing all along on these equilibrium expressions, it's products over reactants. In this case, water is a pure liquid, so it's 1, so it doesn't show up in our expression. There's no coefficients in front of any of the molecules in our equation, so everything is just the concentration. It's just to the power of 1. So we have ammonium ion times hydroxide ion divided by ammonia. And so that equals our Kb value, which we're told is 1.8 times 10 to the minus fifth. So those first two steps, writing the dissociation equation out, and then the equilibrium expression, same approach as what we did with the weak acids. Hopefully by now, setting up this table here with initial concentration, changing concentration, and equilibrium concentration, hopefully that's getting to look pretty familiar to you. So we go ahead, we have our reactants and products listed out on top here in molar concentrations. And then we go ahead and start filling in what we know. Well, we know initially we have 0.15 molar ammonia, and then the ammonium and hydroxide ions start out as 0. Then there's going to be some change as that equilibrium gets established. And so some amount X will get reduced from the 0.15, some amount X will form for the NH4 plus and the OH minus. Then we re-express that as the equilibrium concentration, 0.15 minus X, X, and X. So the next step is going to be, we're going to take what these values are and just plug them into our equilibrium expression. And so what we'll get is, we'll get that KB value equals x squared, because we have x times x, divided by 0.15 minus x. Just as we did with the weak acids, we say by definition, if something's a weak base, this amount that's going to be lost from what we started with, in this case, the 0.15 minus x, that's going to be relatively small. So what I'd like you to remember is if the problem is involving a weak acid or a weak base, don't worry about using the quadratic equation. If it doesn't involve one of those, then you have to use the quadratic equation. And so in this case, we're going to make that assumption that that x value is going to be a lot smaller than 0.15. And so because of that, we're going to ignore the minus x in the denominator and just write it as x squared over 0.15 equals that base dissociation constant. So makes the math a lot easier than going through all that to get to the using the quadratic equation and all that. And then we can solve that x and get a value of 1.6 times 10 to the minus 3. Now remember, with the bases, x is hydroxide concentration. We go back to our table and remind ourselves of that. The x represents hydroxide concentration. So before, with the weak acids, we simply took minus the log of that to get our pH value. Here, we'll go ahead and take minus the log of that, but what that gives us is pOH. And remember, one of the relationships that we learned was pH and plus pOH equals 14. So we can leverage that. We can say if we know the total's got to be 14, we can subtract this, and the pOH value for 1.6 times 10 to the minus 3 is 2.80. So we subtract that 2.80 from it, and we find that the pH is 11.2. So it's pretty much a similar problem as if it was a weak acid type problem. The only thing that's a little bit different is at the end, we need to remember that what we're solving for with x is the hydroxide concentration. So if we're asked for the pH, and rarely do people ask you what's the pOH of something. We're conditioned to think of things in terms of pH for whatever reason. And so rarely will someone say, what's the pOH of that solution? They'll almost always say, what's the pH? So for these weak bases, don't get to the end and then take the log minus the log of that and get, in this case, 2.8 and think you're done. You'd have to then use that relationship between pOH and pH equal to 14 to then get your pH. Okay, any questions about this problem? As I said, hopefully the general idea of what we're doing is becoming a little familiar for you right now. Okay, I'd like to look at a couple of homework problems here. Let me get my paper out here. So the first one I'd like to look at is 16.43. And in that, you're asked to calculate the pH of several strong acid solutions. So we've been talking about weak acids and weak bases. Now this problem involves strong acids. What, in your mind, what should that tell you? There's a simple thing that should immediately come to mind if someone talks about strong acids. This would be true of strong bases also.
It dissociates completely.
Yes, it dissociates completely. And so what that means is it's a strong acid. So whatever the concentration of that acid is, that's going to be the hydrogen ion concentration. Okay, so it makes the calculation a lot simpler. If it was a weak one, then we know only part of that concentration is dissociating. And so then we got to do a little more involved calculation to figure out the pH. But once we see that something is a strong acid, we know that whatever the concentration is of the solution that was made up, that's going to be the concentration of in terms of the hydrogen ion concentration, the pH. So in the first one, we're told HBr is there at 8.5 times 10 to the minus 3 molar. So to find out what the pH of that solution is, since it's a strong acid, we simply just take the pH, do minus the log of that value to find the pH. So if we go ahead and do minus the log of 8.5 times 10 to the minus 3, we get a value of 2.07. The other thing I want to just remind you, when you're doing these types of problems where you're taking logs and stuff like that, as I said before, you take the log of this number, in this case 8.5 times 10 to the minus 3. The number to the left of the decimal, in this case 2, is reflective of what the exponent is. The numbers to the right of it, in this example, 0 and 7, that's reflective of the 8.5. So if you do something and you get pH, in this case of 5, you pressed the wrong button somewhere, because it should be, the first digit should be 2, 3, or 4, somewhere around there. It's going to vary a little based on what the 8.5 or whatever that number is. But you can get a feel for if you're in the right ballpark, if you're taking the log of something, by looking at what that, in this case, 10 to the minus 3 is. Because the log of 10 to the minus 3 minus the log of 10 to the minus 3 is 3. So you know you're starting at 3 just on that part, and then it's going to either be a little bit higher or a little bit lower based on what that leading number that it's multiplied by. Okay, in part B, we're told we have 1.52 grams of nitric acid in 575 mils of solution. So the first one was pretty straightforward. We said, if we have a molarity concentration of a strong acid, then if we simply do minus the log of that, that gives us the pH. These other problems in 1643 are really the same thing, but what you're being asked to do is think back to stuff we learned a while back, but hopefully you're remembering, is thinking about what do I need to do to get information into molarity. So in this case, 1.52 grams of the acid, a volume of solution in mils. So right now my units are grams and mils. Molarity is moles and liters. So I've got to do something to get that gram value into moles, and I've got to do something else to get the milliliters into liters. So if we have grams and we want to get to moles, we should be thinking about a molecular weight, right? So over here on the right, I went ahead and calculated my molecular weight for HNO3. So I have my hydrogen, my nitrogen, my 3 oxygens, and I get a total value of 63 grams per mole. So now I can use that to change my grams to moles, and so my numerator is all set. In the denominator, 575 mils. I know that mils to liter is 10 to the third. It's a 1,000-fold relationship. So I can simply just move my decimal place over 3 places, and 575 mils is equal to 0.575 liters. So then now I have moles in the numerator, liters in the denominator. That's my molarity units. So I'm in good shape there. I go ahead and do the math, and I get molarity value for HNO3 of 0.0420. It's a strong acid, so that's the same concentration of the hydrogen ion. And so then it's just a simple calculation to do minus the log of that value to get my pH value, which in this case is 1.377. So once again, similar to what we did in part A, because it's a strong acid, all we really need to do is get that concentration in moles per liter and then do minus the log of it. A little bit different here because we were given grams and mils to start out with, and we had to get it into that moles per liter type of approach. Okay, let's do another one of these. So in this one, we're told we have 5 mils of 0.25 HClO4, and it's diluted to 50 mils. So same general idea. We're trying to get into that moles per liter so that then we can just simply do minus the log of that hydrogen ion concentration. So we start out and we say we have 5 mils of this 0.250 molar solution. So we want to change the mils into liters, because if it's a molar solution, that's moles per liter. So once again, we use our 10 to the third. So 5 divided by 10 to the third mils gets us into liters. And then that multiplied by our molarity, that gives us how many moles of the HClO4. Then in the denominator, we're told that it was diluted to a total of 50 mils. So our total volume is going to be 50 mils. Once again, we slide that decimal place 3 over to the left, 3 spots, and that gives us 0.050 liters. And so then if we go ahead and do that math, then we get 0.0250 molar as our molarity. Once we have that, once again, it's a strong acid. So our hydrogen ion concentration is the same as that HClO4 concentration. And then we would do minus the log of that value to get our pH value. In this case, 1.602. So our goal in each of these so far has been the same, to get it into moles per liter. The first one was pretty straightforward. We were given it in that term. Second one, we had to do a little bit. Third one, a little bit more. Now the fourth one is a little bit more that we have to do, but the idea is the same. In this one, we're told we're mixing 10 mils of 0.1 molar HBr and 20 mils of 0.2 molar HCl. So now we've got 2 acids. The fact that they're both strong acids is fine because we know they're both going to fully dissociate. So we don't have to worry that they're different acids. They're both going to wind up with whatever their concentration is, it's going to give us protons, right? So let's go ahead and first figure out how many moles of HBr we're talking about. So 10 mils of 0.1 molar, so that would be 10 times 10 to the minus 3 liters. That's got to be in liters because we're going to multiply it by something that's moles per liter. That gives us 1 times 10 to the minus 3 moles of HBr. We're told 20 mils of the 0.2 molar HCl. So once again, 20 times 10 to the minus 3 is that 20 mils expressed in liters times 0.2 moles per liter gives us 4 times 10 to the minus 3 moles of HCl. So what we know now is we know how many moles of HBr were put in there and how many moles of HCl were put in there. So we've got in our denominator, we'll add those 2 numbers up, okay? And then in the numerator, we'll add those numbers up, and then the denominator, we'll add the volumes up. And the volumes just need to be in liters. So The 10 mil is 0.01 liters, 20 mils, 0.02 liters. So now we have total moles divided by total liters to give us 0.16 molar. Once again, strong acid, so that's also the moles, the molarity rather, of the hydrogen ions. So we can go ahead and then do minus the log of that 0.167 value and see that the pH is 0.778. Any questions on any of these? Okay, so once again, the key things to remember, once you see or you're told that something is a strong acid, it fully dissociates. That means that the concentration of whatever that acid was and the hydrogen ion concentration, they're going to be the same. And that makes these calculations a lot more straightforward. The other thing you got to remember, though, is when you're working with this, you want it to be in moles per liter. You want a molarity, right? Because pH is minus the log of the hydrogen ion concentration expressed in molarity, moles per liter. So you may have to do something, whether it be change grams to moles or figuring out how many moles you put in because you added some amount of liquid, things like that. You may have to do some calculation like that to figure out what the proper moles are. And you may have to do a bit of work to get it into the proper units in terms of liters. But once you set all that up, then it's simply doing minus the log of it to get that pH value. Okay. Let's look at 16.55. So in 16.55, we're told that we have a vinegar sample that has a pH of 2.9. So I think you probably remember this from last semester in lab. Vinegar is essentially acetic acid, dilute acetic acid, and we're given the acid dissociation constant for that. And we want to calculate the concentration of acetic acid in the vinegar. So acetic acid is a weak acid. So contrary to what we just did with the strong acids, we can't assume it all dissociates. Vinegars, whether acetic acid is a weak acid. So we're going to have an equilibrium expression for that. So here's what we would do. We would write our equation out. So acetic acid dissociates to hydrogen ions and acetate ions. Then we'd write our equilibrium expression, H plus concentration times acetate concentration divided by acetic acid concentration. Coefficients are all 1 there, so we don't have to put any exponents on anything. And our Ka, we were told, is 1.8 times 10 to the minus 5. So we go ahead and we think about, we were told the pH is 2.90. So if the pH is 2.90, that means 2.90 equals minus the log of the hydrogen ion concentration, which means minus 2.90 equals log of H plus. We do that anti-log, so it's 10 to the minus 2.90 gives us our hydrogen ion concentration, and that's 1.26 times 10 to the minus 3. So we now know what our hydrogen ion concentration is, 1.26 times 10 to the minus 3. We know from our equation, our reaction, that the proton and the acetate are both X, so they're going to be the same. So the acetate ion concentration is 1.26 times 10 to the minus 3. And we know that then if we started with some amount of acetic acid to begin with, we've lost 1.26 times 10 to the minus 3 of that. So we would say that's X minus 1.26 times 10 to the minus 3. We'd go ahead and take those values, plug them into our equilibrium expression. So we get 1.26 times 10 to the minus 3 times 1.26 times 10 to the minus 3. That represents the hydrogen ions concentration and the acetate ion concentration. And then the denominator, we have X minus 1.26 times 10 to the minus 3. So now what we need to do is solve that for X. So if you go ahead and work through the algebra here and you work your way down, you can take a look at that later if you'd like. You get a value of 0.089 molar for the acetic acid. Okay, let's take a look at 1.73. So in 1.73, they're talking about ephedrine. That's the stuff that's in a lot of the decongestants. And they're telling us that if we have a 0.3035 molar solution of ephedrine, it has a pH of 11.33. And then we want to know the equilibrium concentrations. And then we also want to calculate the KB. Okay, so let me move this thing again. So the first thing we want to do is we want to write out our equation. So we have the ephedrine plus water, it then gets protonated. So this is one of those amine bases that we talked about because we see the nitrogen there. And then, so it has the protonated ephedrine and then hydroxide ion. We were told the pH was 11.33. So we can work back through that, just as we did before, and find that if the pH is 11.33, the hydrogen ion concentration is 4.68 times 10 to the minus 12. Is to the minus 12, the pH was 11. Those numbers match pretty well, so I probably didn't mess anything up on my calculator. And then my reaction though, hydrogen ion concentration doesn't show up anywhere in there, does it? It's the hydroxide ion concentration that I need to have information on. And so that's where I can use that POH, pH equals 14 relationship. So I can solve for POH, 14 minus 11.33 tells me the POH is 2.67. I can go backwards through that to calculate out my hydroxide concentration from that, similar to what I just did for the hydrogen ion concentration. And I get 2.14 times 10 to the minus 3. Is there another way I could have done that? Remember, so Ka, so the hydroxide times the hydrogen ion has to equal 10 to the minus 14. Remember, we had that relationship we talked about earlier. So I could have gone that way too. All right, so if we go ahead and set up our table again, so we have 0.035 we start out with, 0 and 0 of the cation and the hydroxide. And then we know how much hydroxide is present. That's that 2.14 times 10 to the minus 3. So I can fill that in. Based on the stoichiometry of my reaction equation, I know the cation for ephedrine is 2.14 times 10 to the minus 3. And I know that over here, the ephedrine, 2.14 times 10 to the minus 3 is how much reacted. So I can subtract that number from it. And that's where I get my equilibrium values. So I do that subtraction, I get 0.0329. And the others are still the 2.14 times 10 to the minus 3. This thing again. And then I can set up my KB expression. So KB simply is products over reactants. All the coefficients are 1, so I don't have to do anything about that. And then I can solve for 1.39 times 10 to the minus fourth. So once again, the base stuff, because we tend to think of things in terms of pH rather than pOH, a lot of times you get information like in this case where you're told the pH of it, so you got to take that pH and switch it over to get it into a hydroxide ion rather concentration. So there's usually that little bit extra work you got to do with the weak bases that you didn't have to do with the weak acids. But other than that, it's a real similar type approach. Any questions about this one? I think that's the last example. Let me see. Yeah. Any questions about this or any of the other ones that I went through? So take a look at some of those homework problems. Make sure you're comfortable doing these types of calculations. As usual, make sure you're comfortable using your calculator. So when we talk about, so we've talked about Ka, we've talked about Kb, so that we have the acid dissociation constant, we have the base dissociation constant. And so if we take a look at those, and this is just a table of the Kas and Kbs for the conjugate acid-base pairs. And what you're going to see is that for conjugate acid-base pairs, Ka times Kb equals Kw. So Kw is what? Anybody remember what that is?
Water.
Yeah, and it's 10 to the minus 14th, right? So Ka times Kb has to equal 10 to the minus 14th. So what that tells us is, if we get one of these, we have Kw, so if we get either Ka or Kb, we can find the other one. Because we know what Kw is, that's 1 times 10 to the minus 14th. If we're given either Ka or Kb, because of this relationship, and once again, this is for a conjugate acid-base pair. So going back to this table, these are examples of conjugate acid-base pairs that we can use that information to calculate. We don't need both to figure it out. So let's talk about acid-base properties of salts for a little bit. So there's a lot of ions that can interact with water, and you can get either H plus or OH minus formed. And these types of reactions where you have stuff interacting and reacting with water is called hydrolysis. And there's a lot of hydrolysis type reactions that occur and all that. We're not going to get into that really in this class, but in general, things reacting with water is called hydrolysis. So when you have something that's a salt and you're trying to figure out, is it an acid or base? You have to look at the cation and you have to look at the anion, you have to look at them separately. Because remember, if it's a salt, it's going to dissociate, right? So now you've got these two things in there. So cations can be acidic or neutral. So what I mean by that is the cation can interact with the water to result in some hydrogen ions being formed, or nothing can happen. The anion actually can be acidic, basic, or neutral. That means some anions can either react and form protons, react with water and form hydroxide ions, or nothing can happen. So we'll go over in a little bit rules kind of governing the cations and anions, which give us a feel for how the particular ones are going to interact with water in this hydrolysis environment. Okay, so let's talk about some anions first. So anions of strong acids are neutral. So a real when I think of strong acids, one of the first ones I think of is hydrochloric acid, HCl. So the chloride ion, Cl minus, does not react with water at all. So you don't get any hydroxide formed from that. So that's an example of where the anion for a strong acid, in this case HCl, doesn't do anything. It falls under that neutral bucket. And that's the case for all the strong acids. Weak acids, okay, so something like acetic acid, for instance, anions of weak acids are conjugate bases, so they actually can create hydroxide in water. And here's an example of that. So here's the acetate ion, C2H3O2 minus, with water. It picks up a proton from some of the water, and then you wind up forming some OH. Now, the thing I'll tell you is, this is a weak base, right? So this is where to understand really how much hydroxide is going to form, it's not going to be a ton. It's not going to be a huge amount because it's a weak base, but there will be some formed. And we'll see some examples in a little bit about what that does. So don't, on this like anions of weak bases, or they're weak acids, that those conjugate bases being able to form some hydroxide, don't think it's making a ton of hydroxide. It's not. It's making some, but because it's associated with a weak acid, and we've said all along, the conjugates of a weak acid is a weak base, but they're both weak. The other one I want to mention is protonated anions from polyprotic acids. And those can work as acids or bases. And that gets complicated because then you got to look at the Ka and the Kb and see which one is bigger. And depending upon which one is bigger, it's going to drive it to either act as an acid or act as a base. So this last one, certainly take a look at it and all that, but I wouldn't lose a lot of sleep over that one because that gets a little bit, it gets a little bit complicated to figure out exactly what's going on that. The first two you definitely should be comfortable with. Anions of strong acids are neutral. Anions of weak acids are conjugate bases, so they create some hydroxide ion in it. The third one, the protonated anions of polyprotic acids, can be acids or bases depending upon the Ka and Kb values. We're not going to worry about that too much. Okay, let's take a look at the cations. So the group 1 and 2 are neutral. And so just to remind you of some of those, that stuff like lithium, sodium, potassium, magnesium, calcium, barium, stuff like that. So if you go back and look at the periodic table, see those first two columns, that's what we're talking about. Certainly the most common ones are like sodium and potassium and lithium and things like that. So those are all neutral. Nothing happens with them. Kind of like we said with the anion on the strong acid. Polyatomic cations are typically the conjugate acids of a weak base. For example, NH4+. And when we say polyatomic cations, all we're saying is like with the ammonium ion, we've got 4 hydrogen atoms, 1 nitrogen atom. That's what we mean by polyatomic. There's more than 2 atoms in it. The transition and just past the transition metal cations are acidic. And we're going to talk about why that is because there's no protons involved. But this is why. It gets a little complicated, I think, is that these transition and post-transition just means the column or 2 right past the transition ones. They form dehydrated cations. And so down here on the bottom of the slide, you see a picture of that. And what happens is the cation, in this case, it's iron Fe+3, and the oxygen of the water bond have an association there together. So on the picture, the red balls are oxygen, the white balls are hydrogen, the kind of orangish ball in the middle is meant to be iron. So you get this association that causes some little bit of charge shifting around, and at the end of the day, it can lose a proton, and then you wind up getting H3O+. So different ones of these will make things more or less acidic. And so once again, we're not saying this is like a strong acid or something like that, but you do get some of this depending upon which one it is, and we'll see some values in a moment here. And the result is it's an acidic environment. Here's some of those Ka values. So we see for iron +3, Ka 10 to the -3, chromium 10 to the -4th. We go all the way down to nickel. That's only 10 to the -11th. So you see a pretty wide range of these cations to see how acidic they are. So, iron at +3 with a 6.3 times 10 to the -3 Ka, that's pretty acidic. That's fairly low pH. But you go down to nickel at +2 and 10 to the -11th, well, that's a basic solution, right? So there's some acidity to it, but it's pretty weak. So it varies based on these cations. So in general, if you're trying to figure out what the salt solution is going to do, you got to go through and you got to look at the ions. So just to go over some of these rules, group 1 or 2 metal, cation with an anion of a strong acid, that's going to be neutral. Group 1 or 2 metal cation with an anion of a weak acid, that's going to be basic, because it's going to depend on this fact that the anion's a weak acid. It's the anion of a weak acid. An anion of a weak acid is a weak base. That's that conjugate thing again. Transition/post-transition metal cation or polyatomic cation with an anion of a strong acid. That's acidic. And then finally, post-transition metal cation or polyatomic cation with an anion of a weak acid. That's the one I said we're not going to worry a lot about, because we got to start looking at Kas and Kbs and figure some stuff out there. So this is just a summary of what we were talking about before. Certainly make sure you know the first three. If you want to learn the fourth one, great. But that one, like I said, is kind of a depends type answer. You got to see what the Ka and Kb values are and figure some stuff out. Okay, things that affect acid strength. The proton bonded to whatever it is, and A is just meant to be a generic atom, it must be polarized. So in other words, remember when we talked about polarization, that would be a case of where the electronegativity would be such that we have partial negative charge on the A and then partial positive charge on the hydrogen. So that needs to occur. The bond strength, the weaker the bond, the more acidic it's going to be, right? Because if that bond's real strong, you're trying to lose a proton. If that bond is real strong and the proton doesn't want to be lost, it's not going to be a very strong acid. So weaker that bond, the stronger the acid. And then the third one is stability of whatever that anion is going to be. It kind of makes sense that if the resultant anion is pretty stable, then it's probably a stronger acid, because it's more likely for that to occur. And so these are some factors that affect acid strength. Binary acids would just be two different elements in it. And in general, if you look at the periodic table, acid strength increases as you go within a column from top to bottom, and acid strength increases in a row as you go from left to right. And then in here, there's some a little hard to see on the slide, but there are some acid and base dissociation constants listed in there, and you can kind of see. What you really see though is you get down to HBr, HCl, those are our strong acids. They're far over to the right and they're going down the table. Oxyacids are a term used when you have hydrogen, oxygen, and then another element, which is a non-metal. So that's that stuff that's in that upper right-hand corner of the periodic table. So, and in general, as the electronegativity of the non-metal increases, the acidity increases if you have the same structure. So one thing about the oxyacids, and you can kind of read through this, but I think that the simplest way to remember the oxyacid strength is this chloric-based example here, where we have hypochlorous, chlorous, chloric, and perchloric. So in each of those, we have the same three elements. We have hydrogen, oxygen, and chlorine. What's the difference between each of these molecules? They have increasing numbers of oxygen. So the rule with these kind of oxyacids, where it's basically the same stuff in there and you're just adding an oxygen, all you need to remember is the more oxygens, the stronger the acid. If you want to remember about oxidation numbers and calculate oxidation numbers, feel free. You know, personally, I find calculating oxidation numbers not my favorite thing. So I prefer to just remember on a series like this, the more oxygens, the more acidic. Like I said, if you love oxidation numbers, go to it. But for me, it's easier just to remember more oxygens in a series like this, the stronger the acid. Okay, so now we talked a little bit about organic chemistry stuff when we said the amines and the nitrogens and bases. In the acid side, carboxylic acid groups, and a lot of times that's represented by this COOH designation. Those are acidic groups. And so those are some type of weak acid always. Probably the better picture is down here at the bottom. And the red is the carboxyl group. And so what you would have is you'd have a carbon atom, double bonded to an oxygen, single bonded to another oxygen, and typically where it has the negative, there is a proton there. And then that proton is what is either on the molecule or it deprotonates and it donates that. And it donates and it gets this negative charge. This picture at the bottom is just showing something called a resonance structure. Resonance just means that it can exist in either of those two forms. When things have resonance, in general in chemistry, that stabilizes things. So that's why that's a big deal for the organic chemists in the world. But the key thing is these carboxyl groups, this COOH group, it's real common to donate that proton. And that's where, to understand how easy it is to donate that proton or not, that gets back to the pKa and understanding what that is. Okay, so everything we've been talking about with acid-base chemistry has centered around moving protons, either picking them up or losing them and things like that. There is another type of acid and base definition, which does not involve the protons. And so it's called Lewis acids and Lewis bases. And Lewis acids are compounds that can accept a pair of electrons, and bases are electron pair donors. The Bronsted-Lowry acids and bases fit into this category, but not vice versa. Because here we'll be talking about, so here's a couple examples of that. So we look at ammonia. So NH3, we have our lone pair of electrons. The hydrogen can interact with that lone pair, the lone pair site, and form ammonium, NH4+. That would fit into our classic Bronsted-Lowry definition, and we'd say everything's great because we moved a proton around. Well, you also can have a reaction like we see down below here. So in this case, we have ammonia, the NH3 with the lone pair of electrons, but we also have BF3. And yet those things do react in an acid-base fashion. And this is where the Lewis acid-base type chemistry stuff comes into play. What you have is you have that lone pair of electrons interacting with the boron, and then resulting in a nitrogen boron bond being formed. So this is an example of Lewis acid-base chemistry. It's different than the acid-base stuff that we've been talking about all along because there's no protons moving involved in that. When we talk about those hydrated metal cations, remember we talked about them a little bit earlier. That's another example of Lewis-base chemistry going on. So we have that hydrated metal cation, and then the higher the charge, the stronger the water metal bonds, and that makes it a stronger acid. So this is another example of it, of taking advantage of electrons available to do things. So I wouldn't spend a lot of time worrying about Lewis acids and bases. I think you want to be aware that we mentioned them. I think you want to be aware that Lewis acids are electron pair acceptors. Lewis bases are electron pair donors. But in all honesty, getting into Lewis acid-base chemistry is outside the scope of this class. Go on and take organic chemistry and you'll get a bunch of that fun stuff. So like I said, if don't spend a lot of time worrying about ammonia reacting with BF3, I guess is what I'm saying. And I wouldn't spend a lot of time worrying about this part either. Okay, any questions on anything before I go over just one? I think there's one homework problem I wanted to just go through. Yeah. Okay, let's see. 16.7.5. Here we're told that phenol has a Ka value of 1.3 times 10 to the minus 10, and we're going to write out the acid dissociation reaction and then calculate the Kb for the conjugate base and then decide how strong of an acid it is. So here's phenol, C6H5OH. That can deprotonate to C6H5O minus and then give us a proton as well. So we write that. We know from what we saw, the things we said is that Ka times Kb equals Kw. We're told Ka 1.3 times 10 to the minus 10. We know that Kw is 1 times 10 to the minus 14. So then we can easily solve for Kb as 7.7 times 10 to the minus 5. Okay, so that stuff, just wanted to refresh your memory that Ka times Kb equals Kw. Wanted to talk a little bit about writing one of these equilibrium dissociation equations out. And then finally in C, we're asked, is it stronger acid than water? Well, we were told the Ka is 10 to the minus 1.3 times 10 to the minus 10. Water is 1.0 times 10 to the minus 14. 10 to the minus 10 is more concentrated times than 10 to the minus 14. So that tells us that it's a stronger acid than water. Well, at 10 to the minus 10 versus 10 to the minus 14, that's not saying much, but it is a stronger acid than water. Okay? So that wraps up chapter 16. So let me pull up chapter 17 and we'll get started on that. So hopefully everyone on Zoom can see the chapter 17 slide. And as you can see, it's more equilibria. So not finished yet. And so in this last chapter, we were looking at acids and bases. We talked about strong acids and bases and how we treat those. We talked about weak acids and bases and how we treat those. And we're getting pretty good at doing some of these calculations, right? Well, there's a few other things that can be there in the solution that changes the calculations a little bit. And so that's what we're going to do. We're going to look here and kind of see what some of the effects are. And one of the things we're going to talk about is buffers. So people use the word buffer all the time. They use it in chemistry, you use it in just everyday language a lot of times. And so we're gonna go into buffers, and there's some special things about buffers that we're gonna discuss. So, and part of that centers around buffer is related to something called the common ion effect. And so if you have a weak electrolyte and a strong electrolyte that share a common ion in the solution, the weak electrolyte will ionize less than if it was in there by itself. So what that means is, let's take our friend acetic acid for an instance. You have acetic acid, it's a weak acid, it's going to dissociate to a certain amount of acetate ion. If I added some just acetate in there, say sodium acetate or something like that, a strong electrolyte that fully dissociated, that would then add to the amount of acetate ion I had in the solution, and it's going to do something to the equilibrium. And we'll see in a moment how we calculate that. But that's really what the common ion effect is saying. It's saying that it affects the acid-base equilibrium. It does not affect the equilibrium constant, okay? Remember, we're saying those equilibrium constants are constants. That means they don't change, they make the other people change. You know, think of it as like your parents. They say something and you don't like it, you're going to react, but they're not changing their mind probably, right? They're the equilibrium constant. And so in this case, you've added that common ion in my example, the acetate. And so it's going to mess up those constants. It's going to mess up that products over reactants, that math, but what that equals doesn't change. So the stuff within that equation have to modify in order to still meet whatever that equilibrium constant value is. The other thing we'll see is adding that ion in, it can affect solubility as well. And that's actually a trick that sometimes people will do if they want to precipitate something out or things like that. So here's acetic acid, here's what sodium acetate is. Sodium acetate, as I said, is a strong electrolyte. And just to remind everyone, we know acetic acid is a weak acid up here because it has the double arrows, right? Double arrow means it's going both ways. Down here, sodium acetate just has an arrow going one way. That's how we know that's a strong one. It's just, you put it in water, it dissociates. So remember those little arrows, those do mean something. Okay, so if this is our equilibrium reaction, our equilibrium expression, we have the acetic acid, hydrogen ion, acetate ion. We know that if we add something here on the right, in this case the acetate ion, it's going to shift the equilibrium a little bit because we want to lower that hydrogen ion concentration. To get that ratio of products over to reactants, that's going to move around the concentrations to get it back to whatever the K value is. So let's go ahead and work through an example of what this would look like in a problem. So in this case, we want to know what's the pH of a solution made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate, and it's in a 1 liter total solution, okay? The 1 liter makes it a little easier because we're already just in molarity there. And so here's our equation, of course. Acetic acid, hydrogen ion, acetate ion. So that expression then would be the hydrogen ion concentration divided by the acetate ion concentrate times the acetate ion concentration divided by acetic acid equals our Ka for acetic acid. All right, we go ahead and set up our table that we love these days because we've been doing this for a while. On the top, we've got the reactants and products. On the left-hand side, we've got initial concentration, change, and equilibrium. Initial is 0.3 for the acetic acid, 0 for the proton, and 0.3 for the acetate. And then we have a change. Some amount of this acetate is going to dissociate, gives us X formed and X formed. We go ahead then to get our equilibrium concentrations. And so we subtract that X from the 0.3. We have X for the proton, and then we have 0.3 plus X for the acetate. So what we'll do is we'll take those equilibrium values and we'll plug them into our equilibrium expression. Okay, so if we do that, we have X times 0.3 plus X divided by 0.3 minus X. We're going to go ahead and think back to our thought process when we were talking about weak acids and bases before. And what did we say about that is, we said, well, when we get in these type of expressions, if it's a weak acid or base, we're not going to worry about that little bit that's reacting, especially compared to the number that we're starting with. So that allows us to make this a lot easier because we're going to ignore the plus X and we're going to ignore the minus X. And so we just finally have X times 0.3 divided by 0.3. So it's pretty easy math. Even I can do that one in my head. And it's 1.8 times 10 to the minus 5. And then we go ahead and take the minus the log of that to get a pH of 4.7. So I just want to point out that we're neglecting those plus X and minus X because relative to 0.30, it's not significant. We're not saying that nothing happens. Okay, something is happening. Those are changing, but we're just saying in terms of the size of that value, it's not going to, by the time we round to our significant figures, it's not going to make a difference. But we're not saying nothing happens. Okay. Weak bases, exact same thing. Okay. The common ion shifts the equilibrium back to the reactants if you added here something here on the product side. And just as we talked about weak acids and bases before, is the same thing with some of these properties as well. They behave similarly. Okay, so that leads us to buffers. So what is a buffer? A buffer is a weak conjugate acid-base pair. And what's unique about the buffers is that you can add a little bit of acid or base to them, and the pH really doesn't change. Technically, it changes a little bit, but it's not a noticeable change. And I don't remember if it's in one of the examples or one of the homework problems where there's a calculation where you add stuff to water and you calculate the pH, and then you add it to a buffered solution. And that's where you really see the buffered solution changes a little bit, but the water itself changes dramatically. And that's really what you're doing with buffers. Buffers have the ability to accept a little bit of acid or base, depending upon what type of buffer it is, and you don't see any significant pH change. Now, a couple things about when you have buffers. The solutions are relatively high concentrations, and we're defining high concentration as 10 to the minus 3 molar. And you think about that. Why does it have to be a relatively high concentration? Because remember, when we neglected these things before, we said, oh, compared to what we started with, it's a really trivial amount. So if that starting amount isn't big enough, then it's not going to be trivial. The other thing is you need the concentrations of the conjugate acid-base pair for each of those concentrations to be roughly the same. Okay, it doesn't have to be exactly the same, but it's got to be kind of in the same ballpark. Okay, and so that is what allows you to have a buffer solution. And there's some specific calculations that we can do pertaining to buffer solutions. And we'll talk about that in a few minutes. There's two ways you can make a buffer. One is you can take a weak acid and then take the salt of its conjugate base. So in other words, for using our acetic acid example again, you can take acetic acid, and then you could take some of that sodium acetate and have the acetic acid concentration and the sodium acetate concentration be about the same and mix them together, and then you'll get a buffer. The other way you can do it is you could take, in this case again, you could take a strong acid or a strong base, depending upon where you're at, and you can neutralize something, okay? So it's done both ways. It's done both ways. I'll just leave it at that. So how does the buffer work? As I said, you add a little bit, you have your initial buffered solution, you add the hydroxide, you get a little bit of increase in pH, but it's relatively small. You add the acid, you get a little bit of increase, it's relatively small. Once again, we're not saying that it doesn't change, it just changes a tiny bit and it's not usually considered significant. Okay, so how do you calculate the pH of a buffer? Okay, so if we think back about our expression for a weak acid, we write that equilibrium expression as the proton concentration times the anion concentration divided by the acid concentration. So we've seen that expression quite a bit. If we take minus the log of both sides, okay, so on the left-hand side now we have minus the log of Ka. We're going to pull out the hydrogen ion concentration. So by doing that, we have minus the log of the hydrogen ion concentration plus minus the log of this ratio of the anion concentration to the acid concentration. Then we can rearrange this. And by rearrange, all we're going to do is we're going to take this minus the log of the anion divided by the acid concentration. We're going to move it over to the left-hand side here with the minus the log Ka term. Okay, that'll change this sign to plus. And so we can rewrite that as minus the log of the hydrogen ion concentration equals minus the log of Ka plus log A minus over HA. What's minus the log? Anybody remember what that means? What's another way of saying minus the log? It's P, right? So minus the log of the hydrogen ion concentration, that's pH. Minus the log of Ka, that's pKa. And then plus log of those ratios of those concentrations. Well, pKa's, we can look those up in tables. So this is why this gets rearranged to this form. pH equals pKa plus log of the anion concentration divided by the acid concentration. This is a real famous relationship known as the Henderson-Hasselbalch equation. It only applies to buffers, okay? And so don't use it for anything other than buffers, but it's real useful for buffer stuff. Because when you talk about buffers, one of the things that people are concerned about is, well, how good is the buffer? And we'll talk about that in just a moment here. Let me just see something here. Okay, I'm going to go through this and then we'll end for the day. Okay, Henderson-Hasselbalch equation. We're saying what's the pH of a buffer if it's 0.1 molar, 0.12 molar lactic acid and 0.1 molar sodium lactate, and it gives us the Ka for lactic acid. So we can plug in our Ka here. We can plug in our lactate ion concentration here in the numerator, and in the lactic acid in the denominator. We get log 0.1 over 0.12. Over here, that P, remember that pKa means minus the log of whatever the Ka value was. And then we can solve that, and it's a real easy way to tell us what the pH of that solution is. In this case, 3.77. All right, when we pick up next time, we'll talk about buffer capacity and some other things. So just to remind everyone, once again, next Thursday will be exam 3, covering chapters 15, 16, and 17. All right, thanks.